But what is category theory? To understand that, let's first understand what a category is. A category is a collection of objects and connections between them. A connection maps object 1 to object 2, and in category theory, we call these objects categories and the connections morphisms. These could be functions between sets, linear transformations between vector spaces, or row operations between matrices. What is category theory? Category theory is an abstract field exploring and delving deep into how categories interact with each other. In this, we try to abstract out from the intricate details of whatever the category might be and view it at a larger scale. For example, we abstract out of sets to not care about the elements within a set or what they are, but rather to a black box with the only metric being the number of elements or the cardinality of the set, which resultingly decides the size of the black box. Let's start from the basics. A set is a collection of objects, and it could be anything. The collection of all natural numbers, the names of all items in a warehouse, and so on. For now, let's look at the set X containing numbers from 1 to 5. Now, let's say that we have a set Z with the numbers 1 and 2. Now, as we can see, that for each element in Z, that is the same element in X. So, we can say that Z is a subset of X, and conversely, X is a superset of Z. Let's take a different set Y. The Cartesian product of two sets is all possible orderings of elements within both sets. A relation is a subset of this Cartesian product. A function is a special relation in which each element in one set is mapped to one output in the other set. Here, we can see the function x plus y from set x to set y. There are different types of functions. For example, surjective functions. This is a surjective function in which all the elements in the second set are mapped onto. If we add an element e to the second set, it will not be a surjective function anymore as all the elements are not being mapped onto. Let's look at a different example of this. Let's say we have a function in which two of the elements from the first set are going to one element in the second set. This is called a surjection, which creates what we call partitions in the first set. Let's say we have a different function now mapping the same two elements to a different element in the second set. This looks like a different function, but this is the same as the previous function. We can easily map the previous output to the current output. This is called an isomorphism. When we can map one function's output to the other function's output, we have an isomorphism. Let's take two different partitions now, and we can see that the first set is a subset of the bigger set. And we denote this with a less than equal to sign. This is called a pre-order. Establishing this order in sets also makes it a poset or a partially ordered set. Let's take a different example again. Let's say that we have a set with the partitions showing if n people are connected. We can see that there are two people in the first set who are connected and two sets of two in the second set who are connected. And we want to find out if the persons in red are connected to each other. While they are not directly connected to each other in both the sets, we can see that when we join the sets, they are connected. This is called the join or the union. And the effect that we just saw is called a generative effect. This was a brief introduction to category theory and is heavily inspired by the book written by Spivak and Ponk. Thanks for watching.